Greetings everyone, this is Mr. Mullen. In this final podcast, I'm going to be talking about some complex circuits and how to address these problems. So to get us started, I want to do a little warm-up, and you can perhaps pause this video and try to really think about how you could figure this out. The question is, how do the currents through the three resistors in the circuit compare? How do the voltages across them compare? Okay, take a second to pause this video, try to think through this, and then come back in a second. Alright, now that you've taken a chance to kind of work through this, we want to look at how the current and the voltages compare through the entire circuit. And so what I'm going to have to do is I'm going to have to kind of take as a starting point, we've got the circuit as a whole, and as current is flowing out from one end of the circuit, it's going to, in this case, we've got some parallel branches. So it looks like some can go this way and some can go that way. Now because it looks like the resistors or the resistance in each one of those branches is not identical, then current is not going to flow in equal amounts through each path. So my current gets split down each path, and what we have to do is we have to compare voltage changes and current changes and resistance. So we've got to really kind of use Ohm's law to the max here in all these different cases. So one thing I'm going to do is I'm going to kind of color code this so we can kind of try to visualize what's going on. I'm going to choose my my blue for the kind of the bottom end of the negative end of the battery, the lowest energy situation, and I'm going to go ahead and draw blue until I hit something that would have caused its energy to drop. I'm going to choose red here. And I'm going to go ahead and draw until I get to a resistor where I could potentially lose some of that energy. So there we have the highest and lowest energy, and therefore I'm trying to figure out some voltage changes. Then I hit a 7 ohm resistor. If I go down the top path, I'm going to lose some energy. And then I hit a 3 ohm, I'm going to lose the rest of the energy. Okay. So just before I even get to the math of this, thinking from my analogy, we've got our battery is kind of energizing and recycling charge as it goes through. If I go down the 12 ohm path, I'm going to lose it all in one spot, and then as I go down the other one, I'm going to lose some at the 7 ohm, I'm going to lose some at the 3 ohm. So I'm going to go ahead and make the 7 ohm drop a little bit bigger because it's a bigger resistance, and then I've got my 3 ohm drop. Okay, so this is what our battery is doing. And each time we go through one of those resistors, we're losing some of that electrical potential energy. Alright, so the reason why I do this little color coding thing is I want to first talk about the voltage. So how do the voltages compare? And I look at the 12 ohm resistor that is in parallel with the battery, and I notice that it's got all high energy to all low energy. So it has the full 12 volt drop, the biggest color change. In other words, the greatest voltage change. It gets the full 12 volts. Okay. So looking at the other two, which one of those is going to have a bigger voltage drop down that path? And I remember that the voltage using Ohm's law depends on the current and the resistance. So I've got a way to look at the resistance, but now I need a way to look at the current going through. Okay. So looking at just kind of all the current going in this branch here, I don't really know what I is, but because the 7 ohm and the 3 ohm are in series with each other, and they're both kind of on that upper path, they're both going to get the same current. So if the current is the same, then the one with the lowest resistance is going to have the lowest delta V. Okay, and then that makes our 7 ohm going to be the middle. Okay, so just looking at that equation, the I is going to be the same for both the 3 and the 7. And so because it has a lower resistance, it's going to have the lowest 12 volts. So I've got my 12 volt drop there, the lowest delta V. And then I've got my 7 ohm is going to be kind of in the middle. And then now I need to talk about the current. How does the current compare? Okay. So what I need to do is, the current can split down two paths. So I need to figure out whichever path is the easiest to go down is going to be the path that gets the most current. So I've got this 12 ohm resistor the current flowing through the bottom path has to go through the 12 ohm. But for this one here, it's got to go through these two together. So the resistance of that path, when I'm looking at resistors in series, is I just take the sum of the individual resistors. So I've got 7 plus 3, and okay, so I've got my overall resistance in that path is 10 ohms. So when I look and say, okay, which path is going to get the most current flow, it's the one that has the lowest equivalent resistance, and that's going to be the path up top. So we're going to have the most current flowing through these two, because 10 ohms of resistance is less than 12 ohms of equivalent resistance down the other path that it could go. So that's going to get the most current. So the current through that branch is going to be set, and then we've already able to rank the voltage, and then the, when I'm trying to think about that voltage drop, it's going to lose the biggest voltage drop at the 7 ohm with more resistance, and then a little smaller chunk. Whatever that voltage drop is, this one here is going to be the smallest portion of that 12 volt drop that that whole top path experiences. Smallest portion of 12 volts. So if this were a 3 volt drop here, whatever this is, and we could calculate this, then the other 9 volts would be lost at the first resistor. All right, so now we need to take some of these ideas of simplifying a circuit. Now before I go on, I kind of want to show something that I basically did. And what I basically did was I took something that looked pretty complicated, and I actually broke it down into, I said there's 12 ohms in the bottom, and then the top one, it was like those two resistors on top had an equivalent resistance of 10 ohms. So that's kind of what I did, is we kind of looked and simplified our circuit so that we could kind of do a little bit more of analysis. And that's really the hint and the practice for all of these problems. So we're going to do example number 12, and the question says find the equivalent resistance, that means the total resistance of the entire circuit, and find the current and voltage across just the 7 ohm resistor. Okay, so I want to know just there. Now if you want to, you can kind of do a little kind of a color coding ideas just to kind of try to visualize what's going on with voltage. So I'll just do that, and I'm just going to see where my my voltage drops are going to be and what kind of different values I would have. So there's our highest, and then it looks like we've got kind of one little intermediate area here in the center. Okay. So what we're going to do, and this is going to be necessary for all of these types of problems where you've got a really complex circuit. The first thing you're going to have to do is find like the total current flowing through based on the total voltage. So remember I said a second ago, as current can go down different branches or it has to go through multiple things, the current flowing in and out of the battery is going to be divided up among the paths, and it's going to be something we're going to eventually need to have. So I'm going to kind of work backwards. I'm going to start at the bottom of the page and work upwards as I try to take my circuit, and we're going to try to simplify what it looks like and then do some math behind it. So I'm going to look at my circuit here, and I'm going to try to rewrite it. I'm going to start from my positive end of the battery, and I'm going to kind of draw, and I'm going to try to think of, I've got my battery, and current has to flow out, and it's got to go through all these paths. So I'm going to go ahead and draw my first little path here. Okay, so I'm going to have to go through a 3 ohm resistor as I leave going out from the battery. Okay, I hit that. Then I've got a path. I've got some options here. I can either go up to a 7 ohm resistor, or I can go to a 9 ohm resistor. Then my paths come back together. Okay, and then I can go to the other end of the battery. So I've just kind of drawn that circuit kind of in a linear fashion so that I can see all the different paths that are possible. Okay, so I go through the 3, then I've got to go. I'm going to make this a little bit. Give me 1 second here. Okay. All right, well, the next thing I want to do is I want to know about what's going on through this thing here. So to figure out the current and the voltage through that resistor, I know the resistance there, but I need to know the current and the current, I need to know how much of the current gets split down that path. Okay, so to find the overall current, we still need the overall resistance of the circuit. Okay, we already know the overall voltage is 12 volts. So I need to kind of distill this down. So I look at my 7 and 9, and I want to simplify this part of my circuit here. And notice, oh, those two are in parallel. So I'm kind of thinking in the back of my mind here that series circuits, resistors in series for any little branch, I just got to add the individual resistances together. Okay, that's all I've got to do. And I'm thinking in the back of my mind, okay, if there's two stuff that are in parallel, then I've got this little expression 1 over Rp is equal to the sum of all the individual reciprocals of the individual resistors. So I've got kind of these two expressions that I'm going to be looking at, and I'm like, oh, they're in parallel. So I can use that top equation. Okay, so if I take the reciprocal of the sum, if I take the reciprocal of the sum of the reciprocals, so 1 over 7 plus 1 over 9, and I take the reciprocal of that, that's going to give me Rp. That's going to give me the total resistance of those two. So those two little resistors that are in parallel, I'm going to rewrite them as being, it's like current has to flow through a single resistor of 3.94 ohms. Like that's the equivalent resistance of that little mini section of the circuit. Okay. Now remember, I'm still talking about that 7 ohm resistor, which is kind of encapsulated in this, in this calculation. So some of that 3.94 ohms, my current has to flow through kind of that part of it. So I'm just kind of doing that little dotted line to show where our resistor that we're looking at is coming from. Oh, hey, look, I've got these two, the 3 and the 3.94 ohms. They're in series. So now I can kind of simplify that part of the circuit as being like having to go through one giant resistor that has 6.94 ohms. And all I did was add them together. That was just kind of using this first one. I'll just put Rp, this is Rs. Okay, so now what I have is I figured out a way to quickly come up with the equivalent resistance, 6.94 ohms. For these types of problems, you will always have to rewrite your circuit and come up with a way to find the equivalent resistance by kind of breaking all of your things that are in parallel and series and simplifying and simplifying and simplifying until you get one value. Okay, so that's what we did. So now what I'm going to do is that I have the equivalent resistance. Remember, I'm trying to figure out the current that goes through just the 7 ohm resistor. I first need to know how much current we've got to work with total. So I need the total voltage, which I look and see is coming from my battery. Okay, we're going to assume this is ideal everything. And then I can use Ohm's law, and I know that the total current that I'm going to have is equal to the total voltage divided by the total resistance, or the equivalent resistance. So I've got a 12 volt battery, and it's pushing current through a series of resistors that at the end of the day are providing 6.94 ohms of resistance. So I've got 1.73 amps of current that's going through the entire circuit. Okay, now it goes through, and all of we're talking about the resistor in that 7 ohm, okay, which we said was kind of part of this 3.94. So what I'm going to do is I'm going to look and see. I need to know the current that goes through the 7 ohm, but that current gets split. So let's see how much current is actually going to be flowing through that 3.94 branch. Well, that 3.94 ohm branch is in series with everything else, so all the current has to flow through into that branch. That's kind of what I have to work with. So once it goes through there, it has to get split between the 7 and the 9. So how much actually is going to be going down the 7 is what we need to find out. At the end of the day, if I want to find the voltage across the 7 ohm, and I need to find the current across the 7 ohm, I first need to figure out what my voltage is going to be. Let me get my colors here. Across that same part of the circuit. So when I look at my little color coding diagram, and I should have done this a little bit earlier, I've got my blue here. Oops, I got my blue on the wrong side. Okay, so here's my blue coming in. And then we've got and then I've got my red. And I've got kind of my intermediate color. We had the green going on. Okay, so the reason why I wanted to go back and do this little color coding is because I can see that the voltage drop between both sides of my quote 3.94 ohm resistor is the same as the current drop across both the 7 and the 9, because those are in parallel with each other. The voltage drop across any elements in parallel are going to be the exact same. It's felt the same across each one of those. So that voltage drop at the across 3.94 ohms is actually going to be the same voltage across the 7 and the 9. So to find that voltage across the 7, I need to know what that drop is going to be. So to find that voltage drop, I'm going to look at all the current flowing through, and I've got 1.73 amps that has to go through that 3.94 ohms of resistance, and then to find the voltage, that blue to green voltage drop across my 3.94, I can use Ohm's law, and I can figure out that that's going to be equal to 1.73 times the overall resistance going through there is 3.94. And so what we're going to get is a total of 6.8 volts. Okay, so my blue to green voltage drop is 6.8 volts, and I use that by figuring out how much voltage would have to be across that 394 resistor to get that much current that has to be going through the entire circuit. So that's how we can find the voltage across that 7 ohm resistor. Once I know the voltage across the 7 ohm resistor, which is 6.8 volts, now I can use Ohm's law to find the current going through just that 7 ohm resistor. So I take my voltage drop at the 7 ohm divided by the resistance at that 7 ohm resistor, and I've got 6.8 volts being applied across a resistance of 7 ohms. We're going to get 0.97 amps. It's going to go down, and you can imagine if 0.97 amps go down the top one, what the current flow is going to have to be through the other branch, which is going to get that flow split between the 7 and the 9. So more current is going to be flowing through that lesser resistant bulb and less current through the greater one. Okay, so I'm just going to kind of draw some arrows. What I did, I took the amps, kind of taking a step back. I took the overall current flowing through the entire circuit, and as I was kind of going from I got that looking at my circuit as kind of just one resistor. Then I broke it back down and I said, okay, I'm looking for the 7 ohm resistor, which was kind of part of this little parallel branch that had a total of 3.94 ohms. So the current going through that was 1.37 amps, but it got split. So I used Ohm's law to find the voltage across that part of the circuit, and because both the 7 and the 9 were in parallel, that voltage was the same across each. And so that voltage, I'm going to go back here, and then I can use Ohm's law again to find just the current flowing through that branch, or that specific resistor. Okay, I'm going to try another example here, and we're going to, this is example number 13, and I've got another kind of advanced little circuit here. So it says find the equivalent resistance of the complex combinations of the resistor in the diagram and find the current in the 3 ohm resistor. Okay, so we're kind of looking here, and we're just looking for the current going through there, and I want to find the equivalent resistance of this whole thing. So this looks really kind of difficult to deal with, and I'm going to still use my color coding idea, and then we're going to try to simplify this circuit so that we can figure out what it's like as current's going through there. Okay, so I'm just going to kind of do this really quickly. I've got my blue, and then I'll do my red, and this one's a little bit more complicated with the coloring. So then I'm going to kind of go do some alternate colors here. Let's use green. Okay, so these are all going to be the same. And then I'll use a lighter green here. And then I'll use some yellow. Okay. So you can see there's all different kinds, and the bigger the color change, obviously the greater the voltage drop. So I'm going to go ahead and redraw this, and I'm going to try to pretend the current's flowing out from my battery and being forced to go the direction that current would flow. So I'm going to start with red, and we're going to draw current leaving the battery to go through the 6 ohm resistor. Okay. Then I go through the 6 ohm resistor, here I am, and then it looks like, oh, I've got 2 paths I can go down. I can go down this path on the outside here with the 4 and the 5. Okay, so I'm going to go ahead and draw that. I can go through the 4, I can go through the 5, and I can come back together. Or I can go down the center of the circuit and just go through the 3 ohm, and those paths converge. And then before I get back to the battery, I still got to make it through a 2 ohm, and then I can get back to the start. Okay. Now the only thing I didn't do is I didn't mess with the colors here, so I'll just go and add those really quick. So we can kind of get a little visual going on here. So here's my yellow. Okay. And then I've got my green, dark green is here. And I had my light green. And I have my yellow. Right. The reason why I'm doing the color thing is just so you can kind of get an appreciation for how voltages change in a circuit. Okay, so there was yellow, and then we had blue at the very end. Okay, so there's my 2, and I think I've got something weird here. Okay. Alright, so what I need to do now is I need to find the equivalent resistance total. So to do that, I'm going to simplify the circuit and try to break out and simplify some things. So I noticed that these 2 are in parallel, or excuse me, in series, so I can quickly rewrite this as being like having a, and I want to go, this is the one I'm looking at here, that 3 ohm resistor. So this is like having a 9 up here and a 3 down here. Okay, they come back together. I've got to go through the 2 and then get back to the battery. Okay, now I have this other branch in, I've got the 9 and the 3 ohm in parallel, so I can use the reciprocal of those added together, the reciprocals of those added together, and take the -1 of that. And when I do that, I'm going to get, it's like having to go through a 2.25 ohm resistor. And then once I've got them all in series again, I can just add those together, and it's like having to go through 10.25 ohms of resistance. So my equivalent resistance of this entire circuit is 10.25 ohms. And that's just by me having to take the circuit and kind of take all the parallel and series components and just simplify them bit by bit until I can get it into something that looks a little bit nicer. Okay, so I need to figure out the current flowing just through the 3 ohm. So I'm going to start by finding all the current I have to work with, the total. And that's equal to the total voltage provided by the battery divided by the total resistance, which we said was 10.25. And I'm going to get 2.34 amps of current. Okay, so that current is going to be flowing through the whole thing, and that 3 ohm was all part of this 2.25 ohm branch when I kind of simplified it. So that current is going to be, has to go through that 2.25 ohm part, and that's equal to 2.34 amps. So when it goes through that branch, it gets split between the 9 and the 3, but you'll notice that the colors on either side of that 9 and 3 are actually going to be, my yellow and green, they're going to be the same voltage drop because these are in parallel as each other. So they're both going to have the same exact voltage. So I'm going to find that voltage, and that's going to be at the 2.25. It's going to be equal to I times R. And so I can take the current of 2.34 amps times the resistance, the equivalent resistance of those two together, and that's going to be 2.25 ohms. And I'm going to get a voltage drop of 5.27 volts. Okay, that's going to be my green to yellow. And so now that I know the voltage across that 3 ohm resistor, I can find the current. Okay, so this was now the voltage across the 3 ohm resistor is equal to 5.27 volts. And then to find the current going through that little guy, I can take the voltage at the 3 ohm resistor and the resistance there, and that's going to be 5.27 divided by 3, and we're going to get that 1.76 amps is going to be flowing through, not newtons, it's going to be flowing through just the 3 ohm resistor. So having kind of going backwards, the steps were the same. Simplify the circuit so it's basically just one giant resistor. Figure out the total current flowing through it, and then break down, kind of working backwards, where is the resistor that you're looking at, and which kind of area or which branch was it, and then you've got to kind of work your way back to figure out what the overall voltage is across the resistor that you're looking at, and how much current is going through it is something that you can find. All right, I hope this has been helpful. This is tough. Try to work through some of the answer problems and the homework and the extra practice until you get the hang of it, and I hope that this has been helpful.